All right, welcome to the Explainer. Today we're diving into one of the biggest, most mind-bending questions out there, the Fermi paradox. It's this incredible story about huge numbers, a deep cosmic silence, and really what our place is in all of this. So where do we even begin? Well, it all kicks off with this simple but honestly profound question. Picture it. It's 1950, and the physicist Enrico Fermi is at lunch with some of his colleagues. They're all talking about aliens, the high chances of extraterrestrial life, and right in the middle of it all, Fermi just kind of stops and asks, but where is everybody? And you know what? He really had a point. To get why that question is so powerful, you gotta wrap your head around the scale we're dealing with. Let's just start at home. In our galaxy, the Milky Way, we're talking about at least 100 billion stars. 100 billion. And that's probably on the low end. But wait, that's just our little cosmic neighborhood. If we pull back, way back, astronomers think there are at least 200 billion other galaxies out there. I mean, the numbers just start to feel unreal, almost impossible to even imagine. So what does that all mean? It means there have to be billions, maybe even trillions of planets out there that look a lot like Earth. Nice, cozy spots for life to get started. With all that potential, all that cosmic real estate, the universe should be a noisy place, right? It should be buzzing with signals, full of life. But it's not. All we get is silence. And that right there is the core of the paradox. Okay, so how do we even begin to tackle a question that big? Well, back in the 60s, a few astronomers came up with a really clever way to think about it. It's kind of like a cosmic calculator, a framework they built to help organize our ignorance, as they put it. And it's called the Drake equation, named after the astronomer Frank Drake. Now, the genius of this thing isn't that it gives us a perfect final answer. Nope. Its real power is that it takes this giant, overwhelming question, are we alone, and breaks it down into smaller, more bite-sized chunks. So each one of these letters you see here is like a hurdle or a filter that life has to clear to become a civilization we could actually detect. Now, for the first few steps, we're actually getting pretty good at making educated guesses, thanks to amazing tools like the Kepler telescope. But man, the further down that list you go, the more it just becomes pure guesswork. And this is where it gets wild, because this equation is super sensitive. Let's say you're an optimist. You plug in some hopeful numbers and bam, you get thousands of civilizations in our galaxy right now. But if you're a pessimist and you just tweak a couple of those numbers downwards, the answer can drop like a rock, all the way down to one, or even less than one, which kind of suggests that we shouldn't even exist. Crazy, right? So all that uncertainty, it leads us right to our first big idea, our first potential solution to the paradox. What if those pessimistic numbers are the right ones? What if we're not just rare? What if we're a total 1 in a trillion cosmic accident? This is the heart of what's called the rare Earth hypothesis. A couple of scientists, Peter Ward and Donald Brownlee, really champion this. Their argument is basically this. Sure, maybe simple stuff like bacteria is all over the place, but the leap from a single cell to, well, us, that requires a perfect storm of conditions so unlikely it's almost a miracle. And just look at this list. It's like all the lottery tickets Earth had to win one after another. We had to be in just the right spot in the galaxy, not too close to the dangerous core. We needed the right kind of star, one that's nice and stable. We needed a huge bodyguard like Jupiter to deflect asteroids. We even needed our big moon to keep us from wobbling all over the place, which would have made the climate go haywire. I mean, you take away just one of these things, and complex lives might have never stood a chance. Okay, but that's just one theory. Let's flip the script completely. What if the universe isn't empty at all? What if it's just being quiet on purpose? What if they're all out there, hiding from us? Or maybe hiding us from them? This brings us to the zoo hypothesis, which is, yeah, it's as unsettling as it sounds. The idea is that we're not being ignored at all. We're being watched, quarantined. Like there's some prime directive, a strict do not interfere policy, where advanced civilizations are just observing us, maybe waiting for us to grow up a little before they say hello. This isn't even a new idea. Way before it got its official name, the father of Russian spaceflight, Konstantin Tsiolkovsky, basically said the same thing. His take was, why would these perfect animals of the heavens bother with us? It'd be like us trying to have a deep conversation with a gorilla. The gap is just too big. Contact would be pointless, maybe even dangerous for us, until we're on their level. So, you see the two extremes we're dealing with here, right? Is the silence out there because nobody's home? Or is it quiet because we're inside a cosmic nature preserve? Are we alone? Or are we the main attraction? But hold on. There's a third option. One that's, well, it's a lot darker. It hangs over both of these other ideas, and it's called the Great Filter. The best way to think about it is like the final boss in the video game of evolution. It's this one challenge, this one massive hurdle that's so hard to get past that almost nobody ever beats it. It could be anything, the jump from goo to life, or maybe a technological test, but whatever it is, it just filters everybody out. In this, this leads to maybe the most terrifying question in this whole conversation. If this great filter is real, where is it? Is it behind us? Did we already somehow miraculously beat the final boss? Maybe just getting complex life at all was the filter, and we're one of the first to make it through. Or, and this is the scary part, is the great filter still ahead of us? Is it some challenge like nuclear weapons or climate change that we're about to face and that every other civilization has failed? It's a weird thought, but finding life on Mars would actually be terrible news because it would mean the filter is almost certainly still to come. So this whole question of will we make it, it forces us to look at ourselves, at our own future. And there's a really cool way to frame that journey, to think about where we are now and where we could go. It's called the Kardashev scale. It was thought up by a Soviet astrophysicist, Nikolai Kardashev, and it's basically a ladder of progress. It doesn't measure how smart you are, but how much energy you can control. A Type 1 civilization has mastered its entire planet. A Type 2 can harness all the power of its star. Think of a giant Dyson sphere. And a Type 3, well, they control the energy of their entire galaxy. And us, with all our rockets and technology, we're not even on the board yet. We're still a Type 0 civilization, hanging out at about 0.73. Yeah, we've got a long, long way to go. So in the end, the Fermi paradox isn't really about aliens, is it? It's a mirror. It forces us to look right at ourselves and ask, what are we? Whether we're the first, or we're being watched, or we just got lucky, that profound silence out there suggests that what we have here, this noisy, messy, curious spark of consciousness, might just be one of the rarest and most precious things in the entire universe. And the biggest question of all might be, what do we do with it now?